Hello, students. Today we want to talk about two important theorems, very related and very useful to our development of the theory of the derivative. Now, in the previous lecture, we talked about two very important results that we use in combination. That is EVT, the extreme value theorem, and also Fermat's theorem. And usually we abbreviate them EVT and Fermat. Today, what we want to do is talk about Rolle's theorem. Sometimes we'll just call it Rolle's. And then the mean value theorem, which we can say for short MVT. Both of these results basically deal with a hypothesis that is very similar. Rolle's theorem has an additional hypothesis, and the mean value theorem has the hypothesis of Rolle's theorem with an exception of one of the components. So the hypotheses will be very simple to remember, and the consequences of the results will be really, really useful as we continue to develop the theory of the derivative. So let me go ahead and share my screen. When we learn new theorems, just like with the last lecture, we want to use them and use the homework just to practice checking hypotheses. So I think you'll find that this particular section is very straightforward. And like I said before, we will have many good consequences come from these theorems that will help us to unify a lot of the work that we've been doing, and will also lend a foundation to the types of problems that we need to do, for instance, curve sketching and optimization. Now, the very first one that we want to talk about is Rolle. Again, Rolle's theorem. Now, like I said before, the hypotheses are very simple. We're going to start with F being continuous on the closed bounded set and differentiable on the open set. Now, you might be thinking we could just replace differentiability on the closed set for these two and be done with it, since the differentiability implies the continuity. But it is standard to write the hypotheses this way, so we will continue to do that. So again, continuity of F on the closed bounded set, differentiability is not required at the endpoint, so we just say AB, the open set, and the additional hypothesis is that F of A equals F of B, okay? So you can think of this, I've got another sheet here. Oh, here we go. You can think of this type of situation with Rolle's theorem, and I will give you a hint as to what the conclusion is. What it means in this particular case is that there will be a C, a number between A and B, such that we actually have a horizontal tangent. Okay, now that doesn't seem too far-fetched. That means that we have the existence of a horizontal tangent, at least one, when we have the continuity, the differentiability, and F of A equal F of B. And so what I'm showing you here are two different situations. For instance, in the first situation, of course, this is the function F. And again, this red function is the function F. And so if we look at a situation, we're just going to look at this intuitively. If we look at a situation where F is a constant function, that is, say, F equals some number fixed throughout its the interval AB. And so the graph of the function would represent a horizontal line. So that's the simplest case. Of course, the derivative of F, if it's constant, would be 0. And so you could take a C anywhere and, of course, get F prime of C equals 0. So that's kind of the simple case. So constant functions give us a very, very easy way to get the conclusion of the Rolle's theorem. So for instance, you could take a C anywhere in the open interval. So they're an uncountable infinite number. So we would always get F prime of C equals 0 for C in the open interval. So this is when f is constant. And again, remember the constant function is represented by a horizontal line, does not change. Not very interesting. And if that's all we could get, it wouldn't be worth much additional work on our part. So what we want to do is think of, again, the non-constant case. So we'll just say f is constant. And here f is non-constant. Now, this is not a proof, but it's going to give you an idea of how simple the proof is, and it's just a few lines. It's not difficult at all. Now, the idea here, if f is non-constant, then we have a very unique situation. That is, we can now apply EVT because there will now be an extreme value. Okay, and of course, if you notice here, the f of A equals the f of B, so that extreme value must occur or would have to occur in the interior of the interval. And so what I've drawn is just a nice differentiable curve that's non-constant. And since it is differentiable, it must be smooth, and the transitions must be smooth. The differentiability would not allow for cusps or points or anything of that nature. And so if we're just to draw a nice smooth curve that's non-constant, we can generate some horizontal tangents. Now, of course, you can't just draw something and say, well, there's a proof. But what you can see here is with the curve that I've drawn, that satisfies, at least in a visual way, the hypotheses. We see that we have two horizontal tangents. That is, note here, f prime of C1 equals 0, f prime of C2 equals 0. So it's not a surprise with this conclusion. So why do we actually get this? Well, the proof is simple, and I've actually written it out here. This is from your lecture notes, that, again, the use of the EVT is what makes this work. So with the non-constant, the extreme value theorem gives us the extreme value. Say we have a maximum or a minimum, and that is by definition a relative extremum. So we can actually approach the actual value of C in this case that gives the extremum from either side. Now, when we look at this, Fermat says that a relative extremum occurs at what? A critical number. Okay, so if a function has a relative extremum, it must occur at a critical number. So we have that statement here, but we're in good shape now for the horizontal tangent because f is differentiable. Therefore, by definition, f prime of C must be 0. That is, we know the critical number would exist as an element of the domain if f prime of that number is 0 or f prime of that number is undefined. But there's no way that the derivative could be undefined on the interior because of the hypothesis of differentiability. So that's how simple the proof is. But it requires a very precise use of the extreme value theorem. Remember when you have an extreme value, even if it's absolute, it can still be characterized as a relative extremum by definition. And so the proof is very simple and very straightforward. But you think about it, you know, when you actually study the Descartes rule of signs in your prerequisite courses, the proof of Descartes is challenging, but it actually makes good use of Rawls' theorem. So what I would recommend is that you maybe do some investigation and see how the Rawls theorem can be incorporated into the algebra that you learn in your prerequisite courses to effect a proof of the Descartes rule of signs. What we find in mathematics is that we often have to look into other disciplines of math to actually prove results. For instance, you're thinking results in algebra should be just confined to that. Well, we might have to seep into the real analysis, that is the differentiability of a function, to understand certain properties. So if you think about famous theorems in history, it is often the case that new mathematics is invented that sheds light on proofs that were before just impossible to do. So remember, mathematics is a deductive reasoning discipline, where if we invent new items, we want to make sure they're consistent with the items we already have, but these new items may shed light in areas that help us to validate other things that have been impossible for us to do. So again, investigate that if you have some time. Now, the next result, likewise, very straightforward, and we get some nice pictures for it too. This result is called the mean value theorem. Now, when we think about the hypotheses, you notice here we have the continuity on the closed set, and we have the differentiability on the open set, but we are not required to have f of a equal to f of b. Now, the conclusion is this: there will be a C in the open set AB, just like we have in Ross theorem, such that, now this is the kicker, but it's easy to remember, the derivative or the slope of the tangent line at the element of the domain C will be equal to the slope of the secant line that we see is formed from the endpoints. That is, when we consider A, f of A, and B, f of B, we can take these 2 points and form the slope of the secant line that joins these actual 2 points on the graph of the curve. And what the mean value theorem says is that we can find a tangent line that has the same slope as the secant line. Now, you're thinking, well, that's a nice geometric result, and why is it important? Well, the mean value theorem provides some very, very useful arithmetic. Arithmetic is important when it comes to working with the calculus, as we have seen many times. That is, working with limits, working with any type of infinite limit, working with related rates, working with implicit differentiation, the chain rule. Everything has to do with the pluses and minuses and our ability to approach particular real numbers, limiting processes. So what we're going to find is that the mean value theorem gives us a very essential ingredient to the arithmetic of the derivative. Now, in some circles, the mean value theorem, and there are other mean value theorems that we will learn. There are mean value theorems that actually are covered with Riemann integrals, and there are more complicated mean value theorems that can be written about derivatives. But what we find is that as we learn these new ideas, we can now consider them fundamental. For instance, we would look back at what we've learned so far and say that the chain rule is a very, very fundamental result. We can now see that EVT and Fermat are very fundamental, and we will find the same with the mean value theorem. Now, the idea here, and let me just share a geometric situation here, as I did with Rolle. Many times in the calculus, but not all, you can think of the geometry of the situation to lend some kind of intuition. For instance, when we think about the intermediate value theorem, that is very intuitive when we think of it in terms of geometry. Now, it doesn't always mean that the geometry gives us insight or very good insight into a proof, but it certainly helps us to remember the result, and having some way to attach some geometry to a particular theorem, again, enhances our understanding. Now, what I have here is just a very nice differentiable curve. We have the closed set AB. And now what I've done is I have just drawn the tangent line that connects A f of A and B f of B, and draw the secant line. Now, again, this is just a line of sight type thing. Basically, geometrically, we should be able to draw a tangent line for at least one value of C, that is a domain element between A and B. And so what I've done is drawn this tangent line, which appears to give us a slope that coincides with that of the secant line. Now, again, this is just a way to visualize what's going on here. And you might be thinking, well, isn't that a nice result? You know, we get this nice geometry going on. But again, it provides us some invaluable ways to represent arithmetic of the derivative of the difference quotient. So, of course, we use the preservation of sign through continuity with this result, and we have a very, very powerful way to understand arithmetic of the derivative. Now, again, thinking about this gives us some idea as to how we can prove this. In many cases, what we can do is think of creating a function that is the difference between the original function f and that of the secant line. Now, when you think about creating a function, ladies and gentlemen, when you're trying to prove a result, that function may or may not be unique. What is important is that the function that you create actually satisfies the hypotheses and then produces the conclusion that you seek. So this is what makes this particular theorem very straightforward, because it would apply in this particular case that we must use the Rolle's theorem to prove it. So what I've done is what I've just said. If we think of the equation of the secant line here, and we subtract that from the function, we have a function which we simply call h of x. Now, what many mathematicians do is often construct functions and construct objects which they think may shed light on other particular theorem proofs. And that's what we have here. Again, this is not unique, but it works. Often students will say, well, why are we doing this? And sometimes the only conclusion or the only response to that, well, this particular object allows us to satisfy the hypotheses and then prove the result. So we can say it's a means to an end. Okay, now notice, what's nice about this particular function is that we need to check the hypotheses of Rolle's theorem. Now, what's nice about this, if you look at it, we've got the function f itself. We have constants, 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 and then just a linear multiple here, x minus a. So by the hypothesis, f being continuous on the closed set, all the rest of the function algebraically satisfies the continuity, since any polynomial would be continuous on any set defined in the real numbers. So the continuity comes basically for free. Likewise, the differentiability of h comes for free. That is, when we check this, we know that the differentiability of f is given in the hypotheses, and then the rest that's left are just constants and the linear function, and that differentiability is a given because we have our differentiability theorems. So when we create a function or construct one, we simply use what we already know about differentiability and continuity to state that for the given construction. So that part of the process is very simple. It's almost like saying, as I've said here, the continuity and the differentiability follow by hypothesis. Now, all we need to do is show that h of the endpoints will give us the same value, not necessarily a particular value, but a value that coincides between the two. Now, what we find in this case is that when we compute h of A and h of B, we get 0 in both cases. So for instance, in the first computation here, we replace the x with A. So we have f of A minus f of A, which you see here. And then, of course, in this particular component, the x is replaced with A, and we have A minus A, which zeros this term. And of course, this term is 0. So we get a very easy 0 in this case. So we would hope that h of b would give us the same. So now we simply replace, in this case, x with b and get f of b minus f of a. And notice in the next term, we simply replace x with the b and we have the b minus a, which will absorb here. So these two factors absorb. But now when we distribute the negative, we see that the f of b's absorb, and then the minus minus gives us a positive f of a, which absorbs the additive inverse of f of a. So again, we get a 0. So now what we see is all of the hypotheses of Rolle's theorem are satisfied, so we get the conclusion. So by Rolle, there is a C between A and B such that H prime of C is 0. Now, one thing we need to do in order to use this equation is just compute the derivative. Well, of course, the derivative of the constant is 0. And of course, the derivative of a constant times a linear function is just the said constant. So what we get is f prime of x minus the slope of the secant line. So that derivative is very simple. And then what we want to do to get h prime of c equal to 0, we simply replace x with c and set that equal to 0. Now, of course, when we do that replacement here, we just have f prime of c minus the rise over the run. And then, of course, we can just transpose this rise over run to get the f prime of c equal to f of b minus f of a divided by b minus a, or the slope of the secant line. It's amazing how visually obvious, or at least simply obvious, that this particular result is. But we know that we can't just draw a picture and say, well, that's a proof. It certainly gives us some reason to believe that it is valid. And sometimes the geometry will often help us to construct functions that we can use in the proof. So now this section is not overly difficult, ladies and gentlemen, but it apprizes us of some very fundamental results. Again, the existence of a critical number, a horizontal tangent. Again, remember, a critical number of f is simply an element in the domain for which the derivative is 0, a horizontal tangent, or the derivative at c is undefined. And since we have the hypothesis of differentiability, the second portion of the derivative, or the definition of a critical number, does not apply. So we get the horizontal tangents for free, so to speak. And now again, we now think of the mean value theorem as being a replacement of the rise over run. We replace the slope of the secant line with a value of the derivative. So again, that is associating the derivative with some very fundamental arithmetic, okay? So now what I want to do is look at a couple of examples where we just applied these results. Now, what you're going to be able to do in some of your homework is just test hypotheses. That is, you're going to be asked to see whether or not the hypotheses for the theorems actually hold. So that will be just a basic check, which can be easily done by checking differentiability and continuity. Usually those go pretty quickly. And then, of course, with Rolle's theorem, you have to check that the values of the function at the endpoints coincide. So you'll find some of them to be very straightforward, but they will actually help you remember the results. Now let's look at some examples. So in this particular first example, here we have a function that is, we're given f of x equals x times the square root of x plus 9. And what we are to do is determine x-intercepts. Then prove that f prime of c equals 0 for some intermediary value in the domain. So basically, when I say intermediary, I'm saying that we're going to have a value between the two intercepts that will give us the horizontal tangent. So again, just remember that you don't always want to give away the punchline. You just want to say, okay, well, if I can do this and know that Roll's theorem is satisfied, then I should be able to get this for free. So first, let's just notice here, we have a domain of F that will be declared by the radical. So this will be all x such that x plus 9 is greater than or equal to 0. But of course, equivalently, this just says that x is greater than or equal to -9. So this defines the set of real numbers for which this is a real valued function. And then, of course, what we can notice very simply here, just by the zero product, f of -9 equals 0, and f of 0 equals 0. So when we see this, we notice, well, at least we've got some type of closed-bounded set where the value of the function at the endpoints coincides. So we can think of the closed-bounded set -9 to 0. Now, of course, we have an algebraic function which is continuous where it is defined. And of course, this particular algebraic function is defined on this set. So we have f is continuous. So I'm trying to pull the hypotheses for Roll's theorem with the arithmetic of this example. F is continuous on the closed bounded set. Again, when we work through our continuity results, many functions turned out to be continuous where they were defined. Algebraic functions, very useful. Polynomials, trigonometric functions, rational functions. We had so many examples where the continuity was just a direct result from the domain of definition. And now, of course, we can also look at this and see that we have differentiability theorems that also apply. This may be differentiated based upon our theory. That is, this can be differentiated as a product. And then, of course, the second factor can be differentiated by the chain rule. So the differentiability is also assured. F is differentiable on the open set. That is, and we can note product rule, chain rule. So the theories that we have set forth with our differentiability theorems are extremely important now. We don't have to go back to the definition. We can now look at this in terms of differentiability. So in order just to make this a thorough check, let's go ahead and check our derivative. Of course, we allude to what we have to do. So now let's actually write down the actual steps for this. Now, if you like, we can just write this with the 1/2 power. So now by the product rule, the derivative of x is just 1. So we just have x plus 9 to the 1/2 power plus x times, now we apply the chain rule or the generalized power rule, 1/2 x plus 9 to the -1/2. And of course, the derivative of the inner function is just a 1, just so we remember that by the chain rule. And now, of course, if we write this, and you can look at this as factoring. In this case, let's go ahead and factor the x plus 9 to the -1/2. And of course, we can factor the 1/2 too, just to remove all of the things that will end up in the denominator. So we have 1/2 x plus 9 to the -1/2. Now, of course, we have to compensate for this negative power, so we need to write the x plus 9 to the first power and then multiply by 2. And I just won't put anything so you don't think it's a prime. So now, of course, this will give us the 1/2 power of the x plus 9. And of course, the 2 and the 1/2 will absorb to give us exactly what we have here. And now, of course, we've taken all of this away except for the x. So now we can retire some of this to the denominator. Of course, we get the 2x plus x, which is 3x. And then, of course, we have plus a 2 times a 9. And then downstairs, we have 2, and then we have the radical x plus 9. And now we can go here and just go ahead and do a little bit more work. We can factor the 3 out of both of these terms. So we have 3, we have an x, and then, of course, 2 times the 3, that would be plus a 6. So this is kind of a twofer. What we're noticing here is that now, even though this particular function is not defined at -9, we don't need that. We only need the open set. So when you have a particular function, you may be able to intuit from the hypotheses of the given function that you will be covered in the differentiability. But it's good to go ahead and compute that, since we're asked to find the intermediary value for which we get a horizontal tangent. But now we're already good with that. So notice this will equal 0 if and only if the numerator is 0. Of course, the denominator would never make anything 0. That's just undefined. So we get what x equals -6 just by the 0 product. So now, of course, what we're seeing here is that we can set the c equal to -6. So notice again, we have everything that we need. We've got the endpoints of the interval having the same value under the function. We have the continuity on the closed set. We now see, at least in a more precise way, the differentiability on the open set. So we are guaranteed of the existence of the horizontal tangent. And what's nice about this problem is that we can actually find the value. So if we set x equal to -c, this implies that we have f prime of -6 equal to 0. So we set c equal to -6, not -c, and we have the existence of the horizontal tangent. Now, one thing that's interesting about this particular problem here, and I want to caution you, when we talk about these theorems, we talk about EVT, the existence of a maximum and a minimum. We talk about Rolle. We talk about the existence of the horizontal tangent. We talk about the mean value theorem. We have the existence of the tangent line that has a slope that coincides with the slope of the secant line through the endpoints that are given by the closed set that we have. So those endpoints give rise to points on the function, which gives us the secant line when we connect them. So remember, these are existence theorems. Again, they provide us or guarantee the existence of these particular objects. Whether or not we can explicitly solve for them is not the case here. We have the existence of them, and so we can use that fact to further our reasoning in the particular problem that we're doing. It just happens to be the case in certain situations you can actually solve directly for that particular object. That is, in this case, we have the c for which we have the horizontal tangent. So we basically have results of Rolle's theorem. So just remember, existence theorems don't give you a strategy to find these particular objects. That's not the statement of the theorem. The theorem is basically to say that this particular object exists. And that's really often all you need to know, because you can always look for something that you know exists. And if it has to be approximated using approximation methods, then that's fine. Then we just don't go on a hunt looking for something that may or may not be there. So remember, when you work with these in calculus and also in other courses, that the existence may be the only thing that you need. And if certain approximation techniques are necessary, then fine, you can do those. And we will learn about some approximation techniques in this course. One will be called Newton's method. Now, let's look at another example. The next example has to do with the mean value theorem. Now, mean value theorem tells us about the tangent line that has the slope of the secant line. So let's start with a function. We have f of x equals x squared minus x minus 56. And we're given 2 points on the curve, 2 points. We have -6, 14, and we have 8, 0. So what you can see here, let's just do a check. You know, you don't have to believe the statement of the problem or believe anything. Let's just do a quick check of this. Notice we have f of -6 equals, so we have -6 quantity squared minus a -6 minus 56. Now, of course, if you want to look at this from the standpoint of factorization, we can do that. Let's do that. So now notice this is just a 6 squared because the negatives absorb, and we have plus a 6 minus a 56. So you can do this work this way, combine these two. That would be easy to combine. So, or you can factor the 6, many different ways to do this. So we have a 6 times a 6 plus a 1 minus 56. And of course, that's just a 6 times a 7, which is a 42 minus a 56. And of course, the 2 from the 6 is 4. And then, of course, the 4 from the 5 is 1 with the negative. So that gives us exactly what we expected. Oh, excuse me. Let's see here. Where did I drop my negative, or did I just write this down incorrectly? Oh, there's a negative here. Good. I was thinking, oh my goodness. Yeah, that we have a negative there. I'm glad I checked that. That was a typo on my part. So we get a -14. So that should be -6, -14. And then let's check this one. So always check things because you never know if you might have a typo. So let's do 8. So that turns out to be correct. So f of 8 will give us 8 squared minus 8 minus a 56. Now notice again, all of these have 8s in them. You know, we can combine them in many different ways. So in this case, we could say this: we have an 8 times an 8 minus a 1 minus a 56. And of course, this is an 8 times a 7, which is a 56 minus 56, which gives us 0. So these check. So again, one thing that's really important, don't always just take the word for it. You know, when you're doing implicit functions, you know, you really is important. You have a point on the curve. It's always good to check. Do a quick check of these. Again, check that you've written things down correctly by checking the arithmetic, and use good factoring techniques. You can always utilize factoring techniques with numbers because numbers are letters. They're just particular values of the letters that we use to do algebra. So now the question is this: In this particular case, we want the slope of the secant line. So let's do that. So let's compute the slope of the secant line. So we'll just do a rise over run. So just to make the work a little simpler, let's just use this point. We'll do 0 minus a negative 14. So 0 minus a negative 14. And then we'll do 8 minus a negative 6. So this will just give us 14. And of course, 8 plus 6 is 14. So these absorb to just give us a 1. So that's the slope of the secant. Now in the next part, and then the question asked us to go ahead and write the secant line. And what you think we're doing is that we want to find the tangent line that has the same slope. So this will just be a nice application of the mean value theorem. Now, what we want to do, first, let's get the secant line, then we'll go back to the hypotheses. So in this case, let's be lazy. Let's just take that really simple point right there. So we have a slope of 1, and we have a point of 8, 0. So we have y minus 0 equals 1 times x minus 8, the easiest numbers in the world, of course. So we have x minus a y, and then, of course, a negative 8 equal to 0. So that's the slope, or that's the equation of our secant line. And then in the next situation, we want to find the actual tangent line that has the same slope. But now what we can do is just go back to the original here and make some allusions to the hypotheses. We have the closed bounded set, -6 to 8. And we have a nice quadratic function. So we have continuity on the closed bounded set. And we have the differentiability. Again, we can easily differentiate, but we have a quadratic function that we know is differentiable. And this set, it's differentiable for all real numbers, just like we did the last one, even though the derivative gave us the value of C, the intermediary value that we were looking for. So differentiable, well, let me just say that, differentiable on the open set. So again, remember when we talk about the theorem, we're talking about the inputs, the x values, so -6 to 8 right here. So that's why we have this. And so this gives us, that is, these are the hypotheses for mean value theorem, okay? Just like we had before with Rolle's theorem. So we've got those. So now we can find the intermediary value. Now just remember, when you're asked to find these values, it's because the algebra will allow you to do that. Just like I said before, these are existence theorems. And so when you're asked to actually compute these, you will be able to find them. So now we can do f prime of x. So just differentiating the polynomial, don't we wish they were all this easy? 2x minus 1. And so now, by the mean value theorem, we'll have f prime of c equals the slope of the secant line for at least one value of c between -6 and 8. So remember, the mean value theorem doesn't say there's one. There could be more than one. There's at least one. The existence is there. So we have this. So now, of course, this is very simple. So we have 2c minus 1 equals 1. So 2c is equal to 2. So c equals 1. And so we can finish the problem. So at this point, what we want to do is now write the tangent line. So if you think about this, we've got C as 1, so we've got f of 1, will now be 1 squared minus 1 minus 56. Of course, the 1 and the minus 1 absorb, and we just get a negative 56. So if and only if we have a slope in this particular case that we have to know, in this case is 1. And then we have the point, 1, negative 56. So again, it's like everything is given to us. Think about this. We already know the slope of the tangent line here. It's the slope of the secant, but we just had to figure out where it occurred. And we see that in this case, we can just go ahead and mark this off because this is important. This exists where the theorem tells us it does. So we might get other values of C in our calculations, but there may be only one that makes sense relative to the actual interval that we have. So we always need to make sure we've got something that satisfies the results of the theorem. The actual computations are simple. We just have to remind us why we're doing them. So now, when we look at this, we can now finish the problem. So we have what y minus a negative 56 is equal to 1 times an x minus a 1. So we have y plus 56 equals x minus 1. So we can transpose everything to one side. So we'll have an x minus a y, and of course 56 from negative 1 will give us a negative 57, and we'll just set that to 0. Now, of course, when you're doing these problems, it does not matter what form you write them in. If you're just doing the calculation, it may ask you to write them in this form, or maybe to solve for y. Whatever the problem requests, that's what you should do. So just remember when we look at this particular example, just like the Rawls theorem, the check of the numbers is always good, just to make sure you have points on the curve, just as a check for accuracy. Just like needing the negative 14 here to make sure that we actually do have a point on the curve. Then checking for the slope of the secant line, writing that equation, simple point slope, and then going back to check the hypotheses of the theorem, making sure they're enforced. And then, just like with Rawls' theorem, looking at the derivative so we can uncover the value of C, that in this case gives us the element of the domain for which the tangent line slope is that of the secant line slope. Existence, remember, existence. And then, of course, we can actually compute the value of the range of 1 under f to get the point. And then with the actual slope of the line and the point, we can draw the tangent line. So again, this may not be the exact form that is used in other theorems, but the arithmetic that we see here will remind us of how we can actually apply this to other examples. So now we have this difference quotient, again, this difference quotient of the rise over run that now can be configured with a value of the what? Derivative. So we are connecting the arithmetic rise over run with the value of the derivative. So that gives us very important results. And so what our hope is that we can tie certain geometric characteristics of the graph of a function with that arithmetic of the derivative, which we have actually sorely been needing at this point. So I hope that these theorems will be something that you can find fairly straightforward. Remember, just like EVT and Fermat, these theorems, again, give you existence. And Fermat's really, really neat because, like you say, if a function has a relative extremum, it must occur at a critical number. Okay, so again, that says it must occur at a critical number. So that's just saying if there is a critical number, then boom, you've got it. Okay. So again, when you got a statement that ties together something you already understand to give you a result, that gives you more power. Again, and as you see everything coming together, that gives you more power, because now you can make more educated decisions and apply all of these different theorems to solving problems. Again, the whole idea is to be able to use the calculus not only to do math problems, but to do problems in science, engineering, all the entire gamut, so that you can produce good results in your field. Okay, that's all I have to say about this. We'll see you later.